Hello and welcome to lecture number 5. So today we are going to talk about the theoretical insight of rate constant in terms of Arrhenius equation. So in earlier days, like in 19th century, people observed that for every 10 degrees rise of a chemical reaction, if we increase the temperature of a chemical reaction by 10 degrees, the rate increases by 2 to 3 times. So that means uh, the chemical reaction, or the rate constant rather, has to do something with the temperature. So there had been attempt how to relate temperature with rate constant. And therefore in 1889, famous scientist Arrhenius, he proposed an empirical equation. So this equation is known as Arrhenius equation, and it is given as K, rate constant, is equal to some constant A multiplied by e to the power minus E at divided by RT. So we can define these terms. So the constant A stands for the frequency factor, or it is also known as the exponential factor, or rather we call it free exponential factor. Okay. And E act stands for the energy of activation, or simply activation energy of the chemical reaction concerned, and R is the universal gas constant, and T is the temperature in absolute scale. So although this relationship has some limitation, but this had great advantage also. One of the greatest advantage was it was possible to assess the energy of activation of a chemical reaction. How it is done? So if we call this as equation 1, Arrhenius equation, so if we take a logarithm of Arrhenius equation, so log to the base 10k is equal to log to the base 10a minus E act, okay, divided by 2.303 R, and we can say 1 over T. And we can call it equation 2. So the simplest method to measure the energy of activation is we can run the chemical reaction at different temperatures, and we can record the different rate constants. And therefore, if we can plot 1 over T versus log to the base 10k, it would give us a graph, or a straight line, graph of a straight line with an intercept. And from the slope of that straight line, we can figure out the energy of activation. So, in simplest manner, like if someone doesn't want to draw the graph plot, then by some quick calculation, it is possible to determine the activation energy. So this is how we can actually do that. So we have to run the reaction twice, okay, at 2 different temperatures. So one we can call as T1, and another we can call as T2. So therefore, from the equation 2 we have just written before, we can write that log to the base 10 K1 is equal to log to the base 10A minus E act divided by 2.303 1 over T1, and similarly log to the base 10K2 is equal to log to the base 10A minus E act divided by 2.303 divided by multiplied by 1 over T2. So from these two equations, okay, you see, we can easily figure out the energy of activation. So simply we can call it equation number 3, and we can call it equation number 4. So if we do equation 3 minus equation 4, okay, so if we do that, then you see this part will cancel out, and therefore we have log to the base 10 k1 by k2 should be is equal to E at divided by 2.303, and then we have T2 minus T1 divided by T1 multiplied by T2. So by fitting the data T2, T1 and K1, K2, we can solve for energy of activation, E at. So now, one important thing is this A, that means the pre-exponential factor, frequency factor, has been assumed to be constant, or has been assumed to be independent of the temperature T. That is one assumption. Secondly, the question for you, can the frequency factor, that is the A, be evaluated, or can it be calculated from the graph plot? Of course, by the word graph plot means I meant that if someone plots 1 over t versus log to the base 10k. So the fact is there are few limitations of the Arrhenius equation, and later some more developed theories or better equations got introduced, which can successfully relate the rate constant with the temperature. But for this course, that is the undergraduate chemistry course, at this current level, we are not going into the details of the actual or the most accepted relationship of the rate constant with the temperature. But nonetheless, what we understand that we get an idea of energy of activation from Arrhenius equation. So now the question is, how can we define the energy of activation, and is it possible to represent by some diagrams? Okay, so that's what we do next. So before we proceed, just a correction that I missed a negative sign over here. So that should be the final form of the concerned equation. So I'm sorry about that. Okay, so let's proceed. So let's a little bit look into the significance of energy of activation. So according to Arrhenius, that molecules must acquire some energy, and that energy is called the activation energy for chemical reaction. Or in other words, the molecules must be activated. It must contain a certain energy, and that energy acts as a threshold. So once the molecules reach that threshold energy, they can be qualified for the next level of transformation, or basically the chemical reaction. So the scenario can be presented by a set of graph plots, and those graph plots are known as, or called typically, the energy profile diagram. Why this is called so? Because in the x-axis we plot a parameter. This is called the reaction coordinate. So it is very different from the time axis or reaction coordinate or RC, and this is not time. So this reaction coordinate represents the progress of the reaction, and in the y-axis we represent energy, and this energy is basically represents the enthalpy of the chemical reaction. Anyway, so let's assume the energy of the reactant is here. Okay, so I write the word R. So this is the level of the enthalpy, means delta H of the reactants. And we have two scenarios. So one is, we can call it the exothermic reaction, and here we call the scenario as the endothermic reaction. So for exothermic reaction, after the reaction, the product will have lower enthalpy. So that means once the reactant goes to the product, it would release some energy. So that energy level is this much. So this much energy is being released. So this is called exothermic. And in the endothermic, it just the opposite happens. So when the reactant goes to the product, it would absorb certain energy. So this much. So delta H. So this is delta H1 and this is delta H2. So this much energy was absorbed by the reactant. So this is called endothermic. But what happens in between? So remember, we are talking about the activation energy significance, and I have already told you that molecules must acquire some energy. So the reactant molecules, before going to the product, it will acquire some energy level, and this energy level means the highest amount of energy that it must possess before it goes to the product side. So that level has a name, and that is called transition state, and in short this is called TS. So with the progress of the reaction, the reactant molecule must reach to this transition state and then goes to the product. Same here. Sorry. It should go up to here. So molecule has to gain this much of energy, and that is the energy barrier. So this energy is basically known as the energy of activation, EACT. Now the question is, can this EACT be altered? The answer is, well, for a particular route of a reaction, this transition state is fixed, or in other words, this activation energy is fixed. We cannot do anything about that. But of course, we can change the pathway of the reaction by some means, and that process is typically known as catalysis. So what does a catalyst do? So a catalyst, usually it offers an alternate pathway that contains a lower energy transition state, or in other words, it has lower energy of activation. So with catalyst, this is the new transition state, and it has the lower energy of activation. Okay, so EACT star, so here EACT star would be less than EACT. The same thing over here. So the energy of activation can be we have a new energy of activation, rather EACT star, this much, and so this is the new transition state. So the job of the catalyst is to offer an alternate pathway involving lower energy of activation. Okay, And in a process through which this is achieved is known as catalysis. Okay, so our next topic of study is basically catalysis. So now we will move on to the different types of catalysis, and we will study their kinetics in a little bit more detail. So let's come to the major classification of catalysis. It is primarily of two types. So one is called homogeneous catalysis, and the other is called the heterogeneous catalysis. The term homogeneous is defined that when the reactant defined by R and the catalyst defined by C are always in the same phase. Okay. So that means if the reactant is in a solution, the catalyst should also be dissolved in the solution. So both should be in the same solution phase. And here obviously R and C would be in different phases. So that means if R is a gas, then C could be a solid. So let's put some examples over here. So the homogeneous, one of the examples of the homogeneous reactions. So it is enzyme catalysis. And there are many chemical reactions done in the laboratory basis follows homogeneous catalysis. And an example of heterogeneous catalysis, we can tell that the hydrogenation of ethylene gas, okay, and it is done on the solid nickel surface to give basically C2H6. So here the nickel surface acts as a solid phase catalyst, and all these reactants are in gaseous phase, so this is heterogeneous. Now both the homogeneous and heterogeneous types of catalysis are very important for human civilization. First of all, because enzyme catalysis is a homogeneous reaction, and without enzyme catalysis any life would not be surviving on the earth. And then without heterogeneous catalysis it is not possible to do many important industrial transformation. So therefore in this course we will learn both. So we will first start with homogeneous catalysis, and we will focus only on enzyme catalysis, and later on we will take on the heterogeneous catalysis. So let's start with enzyme catalysis. So probably you all know that in a living organism the majority part is water. So therefore when we talk about the enzyme catalysis, so enzyme catalysis undergoes within a living organism, for example human body. So it is basically a homogeneous aqueous phase reaction. Now enzymes are biomolecules, and basically these come under a category of biomolecules called proteins. And the protein molecules are a macromolecule of small segments, and we call them peptide. So a protein basically is a polypeptide, and its structure is very complex. So protein usually takes a three-dimensional tangled up structure, and these strands that I am drawing, these are actually chains of small building block of the proteins, okay, or amino acid molecules linked with peptide bond. So that is the chemical definition of proteins. And there are many thousands, several hundred thousands of amino acids will link each other to form a protein molecule. But the most important thing is, although enzymes being proteins, there exists some particular site. Okay, site means in these twists and turns there exists certain area. For example, an area like here that where I am marking. So this particular area it acts as a groove, and this is also known as substrate binding site. Now, why this is called a substrate binding site? Because whatever the enzyme acts upon, for example, there is another biomolecule M. So this biomolecule is basically a reactant, and when the enzyme acts on this biomolecule, it converts it into the product. So this particular substrate, so this is called a substrate. So this substrate molecule is able to attach only on the particular groove or substrate binding site. So if the molecule doesn't bind to the substrate site, or it goes into any other place, the transformation, that means the catalysis, won't take place. So this groove is very much specific to the geometry of the substrate, and therefore this enzyme catalysis goes through. So I'm writing once again that enzyme catalysis goes through a lock and key mechanism. So I'm now going to explain what a lock and key mechanism is, but from the name you can understand that a good lock should have only one particular key. So and a particular enzyme would act on just one particular substrate, and we can think that the enzyme is a lock and the substrate is the key. So once the correct key is put onto the correct lock, we can have the correct operation. So therefore the lock and key mechanism can be illustrated graphically like this. So suppose we have an enzyme like this. So this is the enzyme molecule, and this is just a cartoon diagram of a protein molecule, and these two kind of ridges I have drawn, these two are the particular groove or the substrate binding site. And then I'm drawing the substrate. So substrate is looking something like this. So you see we have a particular match with this groove. So whenever a correct substrate comes to bind on the enzyme, the groove has to match, and it has to be 100% perfect match. And then we have something like this when the enzyme binds with the substrate, okay, and we call this an enzyme substrate complex, or in short ES. And this binding is reversible, so that means substrate can detach from that binding site also. So basically, once the enzyme substrate complex is formed, then the catalysis happens. That means the enzyme can operate on the substrate and it will give the product. Okay. So after the end of the reaction, the enzyme stays same, but the substrate is now would be converted into the product. So I'm drawing the two products. Okay. So this whatever product P would then go away, would be released from the binding site, and the enzyme would be again free. Okay, so I'm drawing another picture over here. So this is the free enzyme plus the product that goes away, and now the enzyme is free to collect or free to be attached with some more substrate. So this process goes on cyclically, and this process is actually very fast. So there are several hundred steps can take within one single second, and therefore we have an effective formation of the product. Okay, so this substrate without the help of enzyme cannot form the product, and with the enzyme it can form the product, and the product formation can be very, very fast. And in human life, as I have told before, that the role of enzymes, or the catalytic role of the enzyme is undeniable. Means we cannot survive with the enzyme catalysis. Taking from photosynthesis with DNA to the DNA replication, or to the food that we digest, everywhere we require an enzymatically catalytic reaction. So you understand that in our body we have many different types of enzymes. For example, in our saliva we have a particular enzyme, and to digest the carbohydrate food we need a particular enzyme, to digest protein we need a particular enzyme, and even to digest alcohol we need a particular enzyme. So let's erase the board and let's start little bit more about the mechanistic aspect of the enzyme substrate reaction in terms of whatever chemical kinetics knowledge we gained so far. So let's do that. So here I have rewritten the same enzyme substrate reaction into a form of mechanistic steps. So enzyme plus substrate reversibly form ES, and the rate constants are K1 forward direction, backward rate constant is K2, and once the ES is formed, it forms the product following the rate constant K3 plus the enzyme back. So now you see the first step is a reversible reaction or opposing reaction, and from this end to this end it is a consecutive reaction. So this entire enzyme substrate mechanistic steps involve two types of simultaneous reactions, a consecutive reaction and opposing reaction. So I hope now you remember the case that we have described or discussed in lecture number 4, that when such complicated scenario appear, we may consider either one of the two approximations. Now the question is, so for enzyme substrate catalysis, what or which approximation we should follow? So is it the approximation of pre-equilibrium, or we should follow the steady state approximation? Okay, so we have to answer that question first, otherwise we won't be able to solve the rate equation for enzyme catalysis. So first let's consider the pre-equilibrium. Can we apply the pre-equilibrium approximation to this mechanism? So if we remember, the sole condition to be satisfied for pre-equilibrium approximation, we have figured it out last time. Remember, in lecture number 3, the condition is that K2 has to be much greater than K3, or in other words, the final rate constant should be negligibly small compared to the reverse, the backward rate constant. Now look at the enzyme catalysis. If K2 is much higher than K3, so that means once the enzyme substrate complex is formed, it is more inclined to go back to enzyme and substrate. That means it is more inclined to get dissociated rather than forming the product. But in order to have an effective catalysis, we want more and more product and enzyme. So that means here is a problem. So we can eliminate the approximation of pre-equilibrium because the constant condition doesn't give us a realistic scenario. So definitely the method left is the steady state approximation. So question is, how can we successfully apply the steady state approximation? So before we go further, let's assume that if we apply the steady state approximation, so that means basically, you remember the concentration of intermediate is small and appears to remain constant. So therefore, we have to apply this condition, that is ds dt is equal to 0. Now if we apply that condition ds dt, so the rate is equal to dp dt, or the catalyzed rate becomes is equal to k1 k3 multiplied by E multiplied by S divided by K2 plus K3. So this was the equation that we have already seen, right? But here still we have one problem. The problem is we cannot use this rate equation for practical purpose, because why the problem is because it contains an unknown variable E. So this S we can know, okay, because we can measure the concentration of substrate at any time, not a problem. But this E, concentration of enzyme, is unknown to us. So what should we do? But we have one advantage though, that we know the total amount of enzyme at the beginning, E naught. Okay. So at any time of the reaction, the total amount of enzyme E naught should be present at either as unbound enzyme, that is E plus ES. Okay. So we can write it like this: E naught is equal to the concentration of E naught is equal to the concentration of unbound or unreacted enzyme plus the concentration of enzyme present as the enzyme substrate complex. So what we need to do is we need to replace this E in terms of E naught and ES. Okay, but we cannot directly replace it here by saying that E is equal to E naught minus ES. Again, that ES term comes up, and which we don't want to put it here, because again concentration of ES would be unknown. So therefore we have to undergo a certain derivation by following the steady state approximation in order to get a standard rate equation for enzyme catalysis. Okay, so let's clean the board and work that out. So here we go. I have rewritten the mechanistic step once again, and we can express the unreacted enzyme concentration as E naught minus ES that we have already seen, and I call it equation 1. And finally we have to find the expression for rate is equal to K3 multiplied by ES. So I want to express the enzyme substrate complex concentration in terms of E naught or S. So that is my goal. So I want to express that in terms of both E naught and S. Okay, then only I have a complete rate equation. So how to proceed? We should proceed with the steady state approximation. So that means DES dt is equal to 0 is equal to, we can write K1 ES minus K2 ES minus K3 ES. Alright, and then or we can write 0 is equal to K1 ES minus ES within bracket K2 plus K3. So what we do now, here we have E, we are going to replace this E with E naught minus ES from equation 1. So or we write 0 is equal to K1 E naught minus ES multiplied by S minus ES multiplied by K2 plus K3. So or we write 0 is equal to K1 E naught S minus K1 ES S minus ES multiplied by K2 plus K3. So here we see we have two ES terms, so we can take that as common. So or 0 is equal to K1 E naught S minus, if we take ES common, then we have K1S plus K2 plus K3. Alright, so what we can do now, we can replace ES. So or we can find ES is equal to K1 E naught multiplied by S divided by K1 S plus K2 plus K3. Alright, so now we have found an expression for ES here. So we call it equation number 2. So from equation number 2, we are going to put the expression for ES over here to get the final expression for the rate. So let's clean the board and write it over again. So here I have written the expression for ES that we derived a little while ago over here, and then finally the rate is equal to, we get this expression and we call it equation 3. So now you see this is the complete rate equation where the rate is expressed in terms of E naught and S and some whole bunch of other constants. So the people who derived this mechanism is actually a group of two persons. Their name is Michaelis and another person is Menten. So together this mechanism is called the Michaelis-Menten mechanism of enzyme catalysis, and this equation is called the Michaelis-Menten equation. And in order to honor these people, this equation can be transformed a little bit by dividing K1 in both if we divide both the numerator and denominator by K1, we get something like this. And now you see the equation looks a bit simpler, and we have one single constant at the denominator, and this constant is known as K subscript uppercase M, or I write it in a better manner. So Km, and this Km stands for the Michaelis-Menten constant. So or we write the rate of enzyme catalyzed reaction is equal to K3 multiplied by E naught multiplied by S divided by the constant Km plus the substrate concentration S. And this Km is called the Michaelis. So once again I'm writing it, Michaelis-Menten constant, in order to honor those great people for their contribution in deriving this mechanism. So this equation known as equation number 4, gives us the final working form of the enzyme catalyzed reaction according to the Michaelis-Menten mechanism. So we stop here up to this. In next lecture, we will go deeper into this equation and how to represent graphically. That we will follow in the next lecture, and some more interesting topics on enzyme catalysis. So, all right, stay put, stay safe, and I will see you in the next lecture. Till then, goodbye.